I will, because there's only four of us, including me, I'll ask some questions as we go along, or just shout out. You can leave your microphone off mute and stuff if you want, because there's not many of us. So plan today, we're still on this delivering research section of the program, okay? And we're still touching on some of the important skills that you need to actually do a research project. All right, and as I say, statistics. And what we're going to do is we're going to talk about data and different types of analysis for the data, and then go through sort of the real fundamentals. As I say, they're going to see you right for most of your studies. Okay, I see now there's people actually showing up. All right, one sec, guys, and we'll just get them started. I was there, man. I was there. Oh, I see. Okay, hold on, guys, and we'll just expand things. Right, grab a seat quick as we're kicking off. So I was just saying that today is about statistics, which is the most fun bit of research.
Oh, perfect.
Okay, and I was explaining that we can't obviously cover all of statistics in 54 minutes. In an hour we could have done, but 54 no. But we're going to talk about the statistics that should see you right for like most studies that you do. Certainly the smaller scale ones. The bigger ones, you'll have a statistician who will talk you through things. So we're still on the delivering research portion. Can you guys see that well enough? I just can't be asked with it, frankly, because I thought it was just us. So, there you go. Eat the stuff. Okay. It's okay. The slides are kind of bonus material. So we're still on the delivering research and actually doing things. Okay. So we're going to talk about different types of analyses and statistical tests and data and so on, which we all love. Okay. So categories of data, how to clean data, how to deal with some ideas about missing data, hypothesis testing, and statistical modeling. All right, so try and cover it as much as we can do. Charlotte's favorite, statistical modeling.
Yeah.
All right,
That's
so
what she's doing today.
we'll start online. So Kieran, what are the goals of statistical analysis? So why do we bother with statistics at all in our studies, broadly speaking, do you think? Have I gone on mute or something? Are you there, Kieran? All right, she's playing hide and seek. Sultan, can you hear us?
Yeah, I can hear you.
Yeah, so what's the purpose of statistical analysis then when we're looking at data and studies?
To prove, well, you want to make sure that your data is quite reliable and it's robust.
Yeah.
And you want to do certain statistics to ensure that like the result that you're getting is actually true. Okay,
so how might you go even broader than that? And so that, yeah, those are some important bits about doing the study and the analysis. But the goal of statistical analysis is really to look at how an input relates to an output, right? How sort of an exposure, whatever that is, relates to the outcome that you're looking at. And is that a fair summary of what you said? The answer to that is yes, it is.
Do you want them as well to be able to tell you that your output has happened because of your output and not because of something else?
Yeah. So it can tell you that there is an association, and some of the tests can tell you the strength of an association. What else?
That your association is not due to chance?
Yeah, but it's not due to chance. Yeah, so you can see a really strong association just due to chance. You can. Anything else?
If the association is big enough that it's important enough?
Yeah. So it could tell you whether sort of an output or a change in your outcome variable is significant enough to warrant looking at more, or whether it's relevant to a patient and so on. Okay, so these are the sort of goals of statistical analysis, right? So you're looking for the association, we said. You're looking for causation. So association just says, well, these two things kind of climb or decline in parallel, or as one goes up, one goes down, right? But it doesn't necessarily mean that one causes another. So remember way back in the earliest session, we talked a bit about Bradford Hill criteria and so on, determining causation. Well, statistics has a role to play in that. It helps you discover stuff, doesn't it? So you might test a load of different exposures and see which one is associated with the outcome. Okay, and so you're starting to discover new associations for further investigation. And when it comes to modeling, you might be using statistics to build a predictive model to say, well, given X, what's the likelihood of Y? You know, given whatever, given your cat smokes weed, will it get cataracts? To use our earlier model, all right? So, of course, when you're doing your study, you're going to collect data, and we've labored the point about data quite a lot up to now. So there's different categories of data, aren't there? We're all hopefully familiar with some of these. So, Catherine, online, what are some categories of data that you know of, or that you've seen or used?
Qualitative.
Qualitative data, going right at the complex bit. So what's qualitative data?
Qualitative data is usually non-numerical data, which gives us information about usually experiences.
Yeah. Yeah, so you're right. So it doesn't have an ordinal value, does it? You don't say 1, 2, 3, or 4. It's kind of a rich, kind of free text experiential data. And that has its whole own set of tools to analyze it, okay, which we're not going to go into during this course, but it's quite interesting if you're into that sort of stuff, sort of thematic analysis and so on. And it has an important role in mixed methods research, which is a growing sort of school of thought where you combine qualitative and quantitative data together to draw a complete picture of the sort of situation you're investigating. Etienne, what about you? Categories of data, we've had qualitative. Very non-surgical. Etienne's gone because he's frightened. Okay, anybody in the room? Categories of data.
Quantitative.
Quantitative. Okay, yeah, fine. So let's subdivide that because, you know, quantitative is, I might got that at A level.
Ordinal.
Ordinal. So what's ordinal?
A sequence of numbers.
Yeah, so they come in order, right? So, you know, 2 is worse than 1, 3 is worse than 2. Like a scale, like a Likert scale or something. You know, how satisfied are you with your experience today, 1 through 5 or whatever? Okay, what else? What's the most common kind of data we see when we're measuring stuff?
Continuous?
Yeah, continuous. Continuous quantitative data is the most common, isn't it? I think of heights of everybody who works at the trust, or weight. That's probably skewed to the right, isn't it? Okay. Yeah, any others?
Categorical.
Categorical. Okay. So that's quite common. Categorical data, you either have diabetes or you do not, or you are male or female, or you are whatever. Good, yeah. What do you say? Nominal. So what's nominal?
There's no.
Yeah, so you think of that as a you know, you have apple juice, orange juice, pineapple juice or something, and you have a tally for each of those, so kind of nominal data. Yeah, so there's loads of different kinds of data, aren't there? So quantitative. Discrete means you can only be one of a certain number of values. So you can either be 1, 2, or 3, or 4. You can't be like 1.1, 1.2, 1.3, and so on. Continuous, we've talked about. So that, remember, that can be raw or derived. So you can have your weight is 50 kilograms, or you are up the 50th centile for weight or something. So you can derive from that and still treat them the same. There's binary data, okay, where there's 2 options, heads or tails, is an example of binary data. You don't see that too often in medicine, except when it's yes or no, kind of you have the disease or you don't. That's why inclusion-exclusion criteria are so critical, because you either are in or you're out, or eligible or not. And qualitative, as I say, is a whole sort of separate topic in itself. It's really interesting, but is a little harder to describe without doing, if you like. So data is the cornerstone of your studies, right? Whatever size of study or whatever kind of study you're doing. And we, as I say, we talked about data again, but I freestyled some points and thinking about data in my own stuff. So when you are thinking about your trial and thinking about actually doing the work of the trial, whether that's an NIHR thing or an audit of your particular consultant's practice, think about your data type. Okay, how are you going to record each of your variables and what kind of variable is it? Because that will determine what you can do with it later on. And going back and changing it is very difficult. For example, you're collecting data about diabetes, decide, Are you going to collect a binary? They have it or they do not have it. Or are you going to go, well, it's continuous. I'm going to use their, fasting blood glucose. Or are you going to do, I don't know, ordinal? They have, they definitely have diabetes. They kind of have diabetes. They don't have diabetes. They have pre-diabetes. These are all things you need to consider because it will determine what you can do later. Plan your analysis goes closely with that. So try and work out how you're going to answer your question at the end with your analysis, because there are some tests you can't do with some data and vice versa. Over collect your data. Always collect too much data. You don't have to use it all, but if you don't collect it, you can't use it. So as you guys are running the trial, actually delivering the trials, there's way more data being collected than will ever be used and written in the papers, right? So, the powers that be know to over collect. Consider how you record the data. So the reality is on the ground, particularly with smaller scale studies, how you're going to collect the data can make your life easier later. Is it going to be on a spreadsheet? Is it going to be free text? Is it going to be post-it notes? Is it going to be in a file and so on? I've seen it that. And if you collect it as such, if you can organize how that data is collected within that tool from the outset, your life is much easier. If you collect it on Excel and you have a drop-down box, it's yes or no for diabetes, your analysis later is an hour quicker because you don't have to then code all the data. If it's just free text, or if it's just, I don't know how else you might collect it, screenshots of resting blood glucose and so on, it might be more difficult to do that later. And then organize your data collection as neatly as you can from the outset. And don't be satisfied with missing data if it can at all be found. Because again, you have to account for that missing data later and in your write-up, if nothing else. Okay, so data cleaning. So you guys have all seen raw data from a study, right? What does it look like? Friggin' mess. Okay, it's all over the place. There's, different abbreviations used, numbers missing, decimal points missing, all sorts of problems. Okay, it's noisy, dirty, and messy. Okay, it's often got a lot of errors in it. People type it quickly. It's low down the list of things to do in a clinical setting, entering data onto some data collection tool. All right, and there's often outliers. Take, for example, our diabetes study. Someone's fasting blood glucose is normally, kind of, 3 to 7, something like that. And if someone's written it's 70 or 700, there's clearly a massive outlier. There's a mistake there. So it's full of those sorts of things. Your mode of recording, or mode of recording mode, as I've written there, can bring in precision. So if you are using screenshots and so on, you can quite quickly get confused with whose X-ray belongs to who, or whose path report belongs to who, and so on. All right, so you've got some imprecision, and suddenly you're trawling through every path report. If you find one that's wrong, you've got to go through them all, matching them up with your case numbers. Missing data, of course, weakens your case, and you have to decide where your threshold for missing data is. How much data can miss from a case before you discard it or do something else with it? Often you're merging data from different sites, even across this trust, right? 5 hospitals, you're collecting data from 5 hospitals or 5 sets of physical therapists or something. They're all recording it slightly differently. That all has to come together and then look the same. Sometimes you have to transform your data, so turn raw into derived data and so on. So a range of movement in a knee might be recorded as a range of degrees, well, you might need to turn it into a percent or radians or something, if that's what the study determines. And as I say, look for the nonsensical outliers early on. So data cleaning is preparing the data for your analysis, okay? Your statistical tests have no tolerance for dirty data at all. They will only do what you tell them to do. If you give them shit, you will get nonsensical shit out, frankly. And data cleaning is iterative. So you do it once and you think you've done it, you run your tests, they look like gobbledygook, you go back and do it again. So cleaning the data takes time and effort, but once it's done, you will be able to do all sorts with your data. So here's an example of messy data. It's a small chart I nicked off Google. Okay, they all say the same sort of thing, right? The year in question, the city, and the amount of money attached to that. We see how all the data entry points are slightly different. And this is absolutely what it's like in real life. Admittedly, this is exaggerated, but only slightly. And so you can see if you start to run some sort of chi-squared test or something on this, it's going to be too confused because every data is entered differently. So you might take that data and in your mind magnify it by like 1,000, as if you're doing a big study or something. Okay, you have to go through that and tell your program or manually convert it into something that looks more like this. Sorry, we've got the pictures in the way, haven't we? Okay, so every grid is the same. Okay, you're recording the year the same, the city the same, the amount, however you choose to record the figures with or without commas or whatever. And see how I've chosen to deal with missing data. So I know my stats program that I choose to use records missing data as a dot. So as I'm entering data, I record it as a dot. SPSS, I think, just uses a blank cell. Stata uses a dot. R will use something else. Okay, we'll talk about those right at the end, just very, very briefly, okay? So as long as you record it the same every time, your later analysis is much easier. And it's so worth doing it. And I know it is because NIHR studies will employ piles of people across the study to record the data and check it and do it well. All right? So cleaning data, really important, makes life a lot easier. Okay, so when you're cleaning data, you go through your table as much as you can and you start picking apart and you look for outliers and you put them all right and you code all the data and you make all their New York cities say NYC or whatever you're going to do. You then, remember I said it's iterative, so you then can use different techniques to test each of those variables just to double check it's clean and makes sense. So what you can't see so well on this tiny screen in the room, right, is you've got this scatter plot here. And it makes sense, doesn't it? You know, the duration can't exceed the age. So you can't have someone who's only 20 years old having 60 years of diabetes. You can't have someone, you know, you're unlikely to have someone 80 having 0 years of diabetes and so on. So you can plot the continuous data on a scatter graph just to check. And look, you can see here is an outlier. Someone who's about 22 is documented as having 37 years of diabetes. It doesn't make sense, right? So you can find that data entry and either go back to the raw data and check it, or choose to ignore it, or treat it as a missing variable or something. Now in this chart, there's, you know, thousands of data entry points. So the effect of that outlier might be very small. But imagine you're investigating something like Rett syndrome, which is a really rare spinal disorder, a really unusual. You might only have 10 patients over 15 years in a children's hospital. One outlier can really mess up your results and really skew things. So you have to pick these out as best you can early on, okay? And using these tools is useful. So you can look at graphs, plot graphs and scatter graphs with continuous data, the obvious one. You can tabulate categorical data, and if you've got some weird tab, like, you know, you've got diabetes, yes, no, and a question mark, there's only one in the question mark, you know there's some dirty data somewhere. It's dirty, okay? You can look at ranges, so I often do that. What's the range of my recorded duration of diabetes? And if the range is 0 to 10,000, somebody's made a mistake somewhere. You know, it should be 0 to kind of 80 at most if they're born with diabetes. Okay? And look at the consistency. We've talked about, you know, age versus duration, or, you know, if they've been taking an antihypertensive, a new antihypertensive that's only been out for 5 years, but recorders taking it for 15 years, for example. So it takes a bit of time. It takes a good afternoon to think of ways you could test it. The categorical variables is a bit harder sometimes because it tends to be free text, okay? But you can look at tables. You can stratify by subsets. You can say, well, hang on a sec, let's just check, you know, male patients and so on. Well, how many male patients have had, you know, I don't know, mammograms or something? Well, that doesn't make a lot of sense. It might make sense, but actually, if, you know, a huge percentage have, that's unusual, right? So we'll check that data. You can do crosstabs and take out individual variables and so on. So you can look how many people have had, say, fragility fractures, but have normal bone density and so on, and just start to pick out abnormal associations that you know don't necessarily make sense. Okay? So that's data cleaning, and it's really important you do that, and it does take time. This isn't like a 10-minute, oh yeah, it looks fine. You really got to pick it apart. If we've got time at the end, I'll show you some of my programs I do, and most of it is for data cleaning. So after you've cleaned your data, you've invested time like making it make sense and knowing you've got no squiffy data that's going to upset your analysis later on, you then start summarizing your data. And this is really the kind of making friends with your data, getting to know your data. You know, people that you say, oh, you know, what was like the mean in your group? And they go, oh yeah, it was 27.6 years. That's because they've spent some time getting to know their data. And you do it by looking at the table, plotting a few graphs, playing with it a bit, and doing some summary stats. So what's this equation here? Priya, what's this equation on the screen? Priya online. She's frightened
So
of
that's
that.
to work out the mean, so sum of x over the number.
Yeah, very good. So you have to apologise. I don't know what all your jobs are. For all I know, you're a professor of statistics, and I'm sorry if that's the case. But yeah, so,
I know, I'm a med student.
Oh, good. Okay, well, very good for knowing the equation for mean. Yeah, so mean is the sum of x over n. Charlotte knew that already. Okay. Good. So you just start playing with the data and doing some very, very elementary school level maths to it. Okay. So you browse it in the table. You put the table up in front of you and just start flicking through it and looking through it. Are there decimal points in different places? Are numbers bigger, smaller? What's the sort of ranges that you're seeing in your different outcomes and variables? Some data lends itself to a graph. I, for some reason, prefer tables to graphs. Don't know why. You know, you put the graphs up, you do some histograms of your independent versus your dependent variables and see what sort of patterns emerge and so on. And the summary stats, as I say, so central tendency, what's the measures of central tendency? I forgot your name totally. I want to say Tom? Jamie, sorry.
It doesn't matter.
So measures of, so what's the measures of, well, what are some descriptions of central tendency? So you've got, so there's, yeah, so a mean is like the average, isn't it, across the board. And then you've got mode and you've got median. So they're sort of, where is the middle of the data roughly? So an average kind of describes everything together. The median is what?
Median is it's not the middle value.
Yeah, it's the middle value. So if you line up all the data in a row from smallest to biggest, the middle value is your median. What's the mode, Professor Reed? Oh, yeah. It's the most common. So we don't use that one too often, do we? Except in sort of except in sort of kind of interval counting studies, which we don't do too often. But then there's a measure of spread, isn't there? So the data is spread around those central pillars, if you like. So how do we describe that? And that is normal. Good. We'll come on to that. But good statistical words. So we're looking at the spread of variables. So looking at the variation of each point relative to its mean or mode, since we mean the median. So the classic one is standard deviation, isn't it? Yeah, which is a measure of the average distance of the points relative to the average. So it's a roundabout way of saying it, isn't it? You have an average value, and then each data point is a distance from that average value. So what's the average of that distance across the board? Okay. And then there's variations on that theme depending on how you lay your data out, like variance and so on. Okay. And so standard deviation is a classic one. So what's the difference between standard deviation and standard error of the mean? Anybody know that? I'll take that as a yes, but everyone's being kind and letting me say it. So standard deviation is that value, that spread within your sample, within the people you've studied. Standard error of the mean is when you extrapolate that to the whole population. Okay? And that's how we work out, population-wide confidence intervals and so on.
How would you get that number?
I knew you were going to ask that. I can't remember exactly. Something like standard deviation divided by the mean to the power of something else. I can't remember. The computer does it.
Yeah.
All right. But that's an important distinction to make because you need to know that when you're working out confidence intervals and so on. So you can work out your confidence interval for your data. You can also calculate it for the population, standard error of the mean. And then dispersion is a similar idea. It's how sort of long are your tails and so on, which again you can derive from your standard deviation. Ranges go without saying what they are, the biggest and the smallest and so on. Replication, how often does each data value pop up? Is it really common to be 6 foot tall? Is it more common to be 5'5" or whatever? And your distributions, which Jamie said. So what about distributions then? So you're familiar with some of these words? Yeah, normal, binomial, and Poisson distributions. What's a normal? What's your name again? Becca. I'm glad you told me so. I was going to go Roxy, but I went Becca. Don't know why. So Becca, what's a normal distribution?
Just like what you would expect.
Well, so normal is the Gaussian distribution, isn't it? That sound familiar from physio school? No, so it's that bell-shaped. It's the bell-shaped curve. Yeah. So who knows some important features of the normal distribution? Anybody?
We have the majority of people in the middle, but you
Yeah.
have some outliers and some people towards either end.
Yeah, so this is the normal distribution, right? And the great thing about the normal distribution is it's the most common distribution in biomedical sciences, because this is how most like natural data occurs. Whatever you're measuring, heights of trees, weights of people, blood pressures, you name it. Okay? So some really important features of the normal distribution. And the reason it's important that it's normal and why it's called normal is it's the most versatile. We can do the most number of tests to it. Okay, because it's symmetrical, it's smooth, it's beautiful to look at. Okay, so it's normal or bell-shaped curve or Gaussian, they all mean the same thing, all right? So some important features, the median and the mode and the mean are all the same. They're all the same value smack in the middle. Okay, these vertical lines represent the standard deviations. So in normally distributed data, it's symmetrical about the mean. Okay, it's not skewed one way or the other, which means there's a longer tail one way or the other. Okay, and these lines are the standard deviation. So within one standard deviation, plus or minus of the mean, you've got what, just under 70% of the data. Okay, within two standard deviations, you have 95.4% of the data, which is why your 95% confidence interval is plus minus 1.96 of the standard deviation for your sample. For a population, it's the standard error of the mean. Okay, why it's not just two. Okay, so the normal distribution. So what you want to try and achieve if you're looking at continuous data, which most of our studies do, is try and transform your data into the normal distribution. Roxy, what does that mean? Any ideas? So your data could be a different distribution. For example, the Poisson distribution. Okay, and you might plot your data and say, well, I've got all the different heights here, and here's the density or the frequency on the y-axis, and it gives me a funny squiffy curve like this. So there's ways of doing sums to each data point that will then redistribute it to a normal distribution. For example, each, say, height value, you might say, well, if I do the logarithm of that value, then, and plot those, it will be a normal distribution. If I times each value by 2, it will be a normal distribution. It wouldn't, you know. If I square each thing, it will give me a normal distribution. So you might end up with, instead of height on the x, you might end up with, you know, height squared. And as you plot that with density or frequency, you might end up with a normal curve, which means you can do loads of cool stuff to it. You just have to remember at the end to unsquare it, which is the square root. I know you know that. Okay? Does that make sense online? So you want your data to look like a normal curve, if you can. Yes, it makes sense. Sultan, I can tell, is enjoying himself.
What if you can't get your data to a normal curve?
So if you can't, then you have to do different tests to it. And the reason that that is less good is the tests on non-normal distributions of data from your sample are just less robust. They're less sure of the conclusions they can tell you. They're not bad, they're just less sure. We'll come on to it. Okay? So here's another distribution that you see relatively commonly, which is a Poisson distribution. Now this is a counting distribution. So what that means is for each, say, interval at the x-axis, this is a frequency count. So you take your data, you say, well, how many people have a systolic between, say, 1995, 95 and 100, 100, 105, and so on, and you have a frequency, and you then take your total number of data points, and you work out what is the probability of each of my cases having a blood pressure in that gap, say. Okay, and so that probability is plotted on the y, your interval or your independent variable on the x, or your dependent variable, sorry, on the x. Roxy's keen, she's still going in, look at that, all right? And you plot that probability and you get this sort of distribution. Roxy, what is an independent and dependent variable? Because that's where you glazed.
I'm not very good at asking.
That's all right. No, that's okay. Now's the time to ask. And online, if you think of something, just shout it out, okay?
As in, what's the definition of
Yeah,
it?
what are they?
Like something like related to the question.
Okay, good swing. A miss, but a swing. Okay. Anybody else? So the dependent variable is your outcome. The independent variable is your kind of exposure, if you like. That makes sense? You can say no. Yeah, kind of. I believe. I'm convinced, but I don't think Jess is convinced.
So the dependent variable is, when I say we're looking at cell saver in
Yeah.
fracture.
Yeah.
So the dependent variable would be the fact that they had cell saver or how much blood they had or whatever.
Right.
And your independent would be something else. So the fact that they had a different medication as well, or I don't know, something kind of separate, if that makes sense.
Yeah, I think you're saying it right. So you know your dependent is what you're measuring, and your independent is what's fixed. So you know you're male or female. Done. You know your blood pressure is your dependent. That's what you're hypothesizing. That's dependent on your independent variable. That's what I assume. That's how I think of it. That's probably oversimplifying it. That's how I think of it. And your dependent is on the x-axis. Yeah. You strikes me you like that.
Yes.
I've got a good book. It's Penguin's ABC of Statistics next door. Okay, so that's a Poisson distribution. So it's a counting distribution. So if you're counting the frequency of people within a category, this is typically what it looks like. Typically, these are kind of archetypal distributions. All right. So data are counts of events or counts of data points. All right. There's a few important things for the Poisson distribution. Each of those have to be independent. So you can't count in two boxes. Okay, you can't have a systolic blood pressure of 90 to 95 and 95 to 100. Okay? The average occurrence doesn't change during the period of interest. So if you're measuring those over a period of time, then the rate of occurrence doesn't change. So you can't have more people in one group than the other. Blood pressure is not a good example for this. Say you're counting cars on a road. Yeah, and you're going red car, blue car, grey car, silver car, and so on. You can't then do it at a time when the government say all cars are going to be red. Okay, because that then skews your distribution, and suddenly it doesn't count anymore. Stupid example. There should be no upper limit, so you have to essentially have an infinite number of options. So blood pressure is quite good for that. You could have a systolic of 999,000 over a million. It's unlikely, but you theoretically could. But if you draw a line and say it can't be higher than this, you can't get a Poisson distribution properly. Okay, and you use different tests when you're doing this distribution, but we'll talk about those in a minute. So last one to mention is binomial distribution. This is a bit harder to understand, okay? This is where the number of tests you do is fixed and the number of outcomes is fixed. I'm going to use the example of tossing a coin, because it's easiest to understand. If you toss a coin, it can only be heads or tails, right? Every time? Okay, if it lands on its edge, then it doesn't count. Okay, we're happy with that. So it can only be one of two options. That's the bi bit of it, the binomial, okay? Now let's say you wanted to know the likelihood of getting so many tails if you toss that coin 100 times, but no more than 100, only 100 times. That is what the binomial distribution will tell you. Okay, you can only have two outcomes. Each time you toss the coin, it doesn't matter what you got before. It's a whole new test. Okay, and the probability of either a heads or a tails is the same every time you toss the coin, whether you do it once or a million, billion, trillion. Okay, if you plot the results of that on a graph, this is what you get. Okay. So you get this idea that you want to know how many times, what's the probability of getting 150, say, tails when you toss a coin, say, 200 times, then you kind of do the maths to work it out. Okay, my chance is 50-50. The chance of getting two heads in a row is 1 in 4. Chance of getting 3 heads in a row is 1 in whatever. Okay, you plot that on the graph and this is what you get. I struggled this morning to think of an example in medical trials where you would do that. I did. The best I could come up with was if you had a disease that was clearly cured or not cured, and you gave someone, say, an antibiotic for pneumonia, and you said cured means CRP less than 4 and respiratory rate less than 10, okay, and not cured was the other one, and you gave them one antibiotic, okay, cured, not cured. You then gave them maybe another one, cured, not cured. But I can't think of a trial that would do that really, okay? But it comes up in the literature every now and then, this binomial distribution. Again, there's a whole separate set of tests with it, but what you see is this thin, tall spike somewhere along the x-axis, but it doesn't spread out like the bell curve, okay? And there's a limit to what you can do statistically with it. But those are the three that sort of pop up the most, is binomial, and binomial doesn't come up very often. Binomial, Poisson, and normal. There are other distributions, J distributions, F distributions, and so on, that papers talk about when they're talking about we found this distribution and we transformed it into the normal distribution.
Could be like mortality.
I suppose it could be, yeah. We gave them this injection and this many died and this many didn't. The problem with that is your fixed number of observations is then 1, isn't it? Because you can't then, well, they were dead, so then we gave them something else and they were alive again. So that's relatively easy kind of thing to do. But you could do it with, say, I don't know, cancer. I gave them this chemotherapy for bowel cancer, cured, not cured, not cured. Okay, I gave it to them again, cured, not cured, and so on. It's complicated. I found it quite conceptually difficult. The normal one is the one to understand, but I wanted you to hear the other words and at least go, okay, that's a counting one, and that's tossing a coin one. All right, so what do we do with the stuff once we've got it? So we've got all our data points, we've cleaned it, we've become familiar with it. We've looked at our measures of central tendency, we've looked at the means and the medians and the interquartile ranges and all this stuff that GCSE kids do and so on. What do we do now? Well, next we want to do some tests to see if there's any meaning in the data. So far we've done is look at it and get to know it. It's just a big sheet of data, which is fine. What's it telling us? So when I think about statistics, I think, well, I'm either testing a hypothesis or I'm looking for a relationship between the data and I don't know what that could be. So I'm either testing the idea that X causes Y or there's a difference between X and Y. For example, I've given 2 kinds of antihypertensives to Northern European males who are hypertensive. Is there a difference in their blood pressure before, and is there a bigger difference or a difference after they've had a course of the medication? Or I'm modelling, which of course I do for real. But I'm looking at it and going, well, actually, what's the dose of the antihypertensive doing to the blood pressure? And I'm trying to predict what happens to the dependent when I change the independent. When I change the dose of the drug, Roxy, pay attention. All right. What happens to my blood pressure? Got it? Okay. Yeah, I believe you. Now I believe you. You're confident. Okay. Here we go. So what is the p-value, first of all? Kieran, online, what do you understand by the p-value from your experience so far? She gone silent. All right, Sultan. See, this is why. Oh, here we go. Go for it, mate.
Hello?
Hello, we got you.
Oh, it's the I don't know how to explain it. It's like the probability that it's like the probability that a result is like agrees or disagrees with no hypothesis. So it's either like 0.05, or it can be even more like it can be much less than that. I can't really explain it very well.
That's okay. Good go. Good go. Anybody in the room? You're nodding
I was
knowingly.
thinking is if it's like more than 0.05 or something, you accept the hypothesis or reject the null hypothesis, something like
Yeah,
that.
it depends how you construct it.
Yeah, yeah.
So the p-value is the probability that what you found could be due to chance. That's all it means. It doesn't actually tell you anything about the strength of an association or the strength of your conclusion. It just says, well, look, the chance of you seeing this relationship, whatever it is, this difference or similarity, okay, by complete chance, is this. Now, in medical stuff, we choose 0.05, okay? So we choose to accept in our conclusions that all those papers you read, there is a 5% chance, 5 in every 100 times we do this, this relationship would be by chance alone and not a real effect. And when you see papers that say p less than 0.0001, all they're saying is there is 0.1% likelihood that this relationship we're reporting to you is due to chance. It does not say this is a really strong relationship or a really weak one. It just says this is due to chance. If you see a p-value of 0.99, there's a 99% chance of what you're seeing, or 99% probability that what you're seeing is due to chance alone. And we just draw the line at 0.05. 1 in 20. 1 in 20 studies, pick 20 studies out of this month's journals that report a p-value of 0.05. One of them is just wrong. It's just happened by chance. Okay? So yeah, you're kind of right. We set that when we set out in the study. And when you read their application protocols, they said, don't they? Significance level of 0.05. Good studies will say 0.01. You know, do you want to base the fact that you're going to have, say, a pneumonectomy, half your lungs out, okay, on the fact that your study there's a 1 in 20 chance that it's happened by random chance? Don't know, you know? So that the p-value is an important concept, okay? It's about how likely you are to make that conclusion by chance alone. All right, so hypothesis testing. So this is the most common thing we do, isn't it? T-tests, okay? So if you have two independent samples, you've got two groups of people and you're measuring their blood pressures separately, they're not anything to do with each other at all. I've got a group of patients at Mile End in the hypertension clinic, a group of patients at somewhere else, Whipps Cross, in a hypertension clinic. How similar or not are their blood pressures? Is there really a difference in those blood pressures? So if they're normally distributed, which you'll know from becoming familiar with your data, you can do a student's t-test, which compares the means effectively and says, yes, these are different groups, these are meaningfully different groups, or no, they are not meaningfully different. But you can only do that if they're normally distributed with all those important features, okay? Now, you can do a paired t-test where you say, okay, we gave Charlotte, we measured Charlotte's blood pressure on a Monday, we gave her 5 days of antihypertensives, and we measured it on the Saturday afterwards. And we're comparing Charlotte with herself, okay? And if all that data is, if the pre-exposure data is normally distributed and the post-exposure data is normally distributed, then you can do a paired t-test. You're comparing Charlotte with herself. And that's just behind the scenes. What the test does is, rather than comparing just like two lumps of data, it matches each case up and compares the likelihood of this mean versus the likelihood of this mean. All right? Now, what if it's not normally distributed for whatever reason? You've collected all that data and it's a different distribution of some sort. So you can do the same test. You can compare the means of those datas, but we use a different test. And Jamie earlier said, I think, parametric and non-parametric, or normal and non-normal, right? When we're applying tests to a normal distribution, we call that a parametric test. I don't know why, we just do. Okay. If you're doing tests to data that is not normally distributed, it's a non-parametric test. Y'all heard of this stuff, okay? So for every test you can do on normal data, there is an equivalent test you can do on not normal data, but it is not as strong. And you tend to see higher p-values because it can't be as confident. And the way they work is they start ranking the data. So the computer program will rank all the data points, and all the data points in the other group and just see how much those ranks kind of overlap. Like where does this set breach 100 versus this set and so on, okay? The non-parametric equivalent of comparing two independent groups of data to see if they're meaningfully different is the Mann-Whitney-U test. Don't know why. I guess Mr. Mann and Mr. Whitney is always man, isn't it? It's always a person, a male person. Okay, did it. Don't know. Okay. Some programs call it the rank sum. Don't know why Stata calls it the rank sum test. Don't know, because they rank it all and then you add it up and so on. Okay. So if you're comparing two normal sets of data, which is the most common set of medical and biomedical and kind of organic data, t-test or Mann-Whitney-U. That will get you through 99% of studies, actually. Okay. So, like I say, student's t-test. Student was the pseudonym of the guy who made it up. Don't know why. It's for normal, Mann-Whitney-U for not normal data. But it's for continuous data, of course. So what about categorical data? So this is the other big lump of data that I've sort of interpreted in my academic career, short though it's been so far. It's almost always continuous, normally distributed data. So categorical data, if you build a table, you say, okay, male, female, hypertensive, not hypertensive. And you want to see, well, hang on a sec, is there meaningfully more males hypertensive than females hypertensive? Okay. And you need to compare the proportions of hypertensives within male and female, let's say. That makes sense? Yeah? Then you do a chi-squared test. And what that does is it works out the expected number of hypertensives within a group and compares it to the data you have. And to do that, you can imagine it has to make a whole load of assumptions. It has to go, well, I'll assume that hypertension is evenly distributed across the population. I'll assume that it's normally distributed. I'll assume that it's this and that. Okay? And then it compares what it expects to see on your table of male, female, hypertensive, not hypertensive, against what you are seeing. Okay? And then it provides you with a chi-squared value, which is meaningless, and then it gives you a p-value, which if it's less than 0.05, you go, yay, there's a real thing. Okay? So a chi-squared test is how you analyze categorical data to draw conclusions. Now, Fisher's exact test is a derivation of that. Because sometimes when you draw that table, imagine it's male, female, doesn't have Rett syndrome and has Rett syndrome, my rare disease of the day. Some of those might have like one or no cases in them. Like it almost exclusively affects young females, for example. So the chance of you having a male with Rett's is so low, like it's basically nil. If the cell, that box has less than 5 points in it, chi-squared gets confused. The maths doesn't work. Okay, don't need to know why, it's not important. So if any one cell has less than 5, use the Fisher's exact test. It's just a bit more robust to low cell counts. All right, what I normally do is I do them both and see if they're different. If they're different, there's something weird going on, you have to find out what it is. So, continuous normal data, comparing two groups, student's t-test. Continuous not normal data, comparing two groups, Mann-Whitney-U. Categorical data on a 2x2 table, chi-squared or Fisher's exact test. Those 4 tests will do most studies that you want to do. Okay, particularly at Foundation House. I know you guys are dealing with big data sets, but that's the reality. Okay, so what if you've got lots of groups and you want to compare the means about lots of groups? We're nearly done. Now remember I said that a p-value of 0.05 means that there's a 1 in 20 chance that what you're seeing happens by chance. So imagine you have 20 sets of data in front of you, all measuring blood pressures in 2 places, and you did the same test on every one of them. One of those tests, you're going to either fail to see a relationship where there is one, or see a relationship where there isn't. We're just repeating it over and over again, and 1 in every 20 is going to occur by chance. Does that make sense? That's why we can't just keep doing t-test after t-test after t-test after t-test, because you're going to find something if you look hard enough. So then if you've got 3 groups or 5 groups or 20 groups, and you're looking to compare the means of all the groups, you run the risk if you do just group 1 versus group 2, group 3, group 4, group 5, group 6, group 7, and so on, you're going to start seeing things that shouldn't be there. Yeah? I'm trying to walk through it as slowly as I can, but I'm saying the same thing over and over again, I realise. Okay? So there's a test called the ANOVA test, which does that sum for you, but takes into account the fact that if you keep doing t-tests over and over again, you'll see something spurious, you'll see something that isn't really there. So the ANOVA test takes your 20 groups of normally distributed data and compares all of them together and tells you whether there's a real difference or not. Imagine you've measured, Jamie's gone and measured blood pressures in 1,000 people at every hospital in London, probably like 20 hospitals at least, right? And he wants to know, is there a meaningful difference across London, or is basically everybody the same? He takes his groups, they'll be normally distributed because they're organic medical data. He does an ANOVA, and the ANOVA tells him, yes, there is a meaningful difference across all your groups. It doesn't tell you where that difference is. It doesn't tell you if it's between Royal London and Broomfield. It just tells you there is one. Now, if all the data is normally distributed, it's an ANOVA. If it's not, it's called the Kruskal-Wallis test, which is super complicated maths. Make the computer do it. Okay? So then the last test I'm going to talk about, let's say Jamie's got his 20 sets of data, he's done his ANOVA, and it said, yes, Jamie, there is a difference somewhere in these groups, but it doesn't tell him where. What you then do is something called a pairwise comparison of means, which is another sum that the computer will do really easily. And it does that, right, Royal London versus Broomfield, Royal London versus Bath, Royal London versus, Hillingdon, Royal London versus everywhere. Okay, now, Bath versus Hillingdon, and so on and so on. Does all those combinations and will tell you which pair the difference lies in. But the underlying maths takes into account repeating the same test over and over again with a correction. And you can change the corrections if you want. The most common one is called a Bonferroni. Okay? Does that all make sense? So you've got 2 groups normally distributed, 2 groups not normally distributed, categorical data, lots of groups normally distributed, lots of groups not normally distributed. That's it. That will see you through, I think, most studies, certainly until you're doing big multi-center stuff. So what about modeling? Well, modeling is just about using one variable to predict another. And this is where regression sits. So regression is about understanding those relationships between one and the other, and it's a continuous relationship. Okay? So there's lots of different kinds of regression. We're not going to go into it, but logistic is about a yes or no thing relative to a disease. Let's say you've got your fasting blood glucose is a linear scale, right? It can be 0, 1, 2, 3, 4, and all the way up, and everything in between. Somewhere along that line, you have diabetes or you don't, and somewhere you change from one to the other. That's logistic regression. So I just think logic, like left or right, 1 or 0. Okay, so logistic regression is deciding yes or no you have a disease given a continuous scale, that kind of model. Polynomial is where that relationship, that scale, which is linear in resting blood glucose, isn't a straight line. It changes and curves. For example, height. So no one is minus 10 centimeters tall and no one is 50 meters tall. Okay, but you have, say a growth chart which isn't a straight line. You're slow when you're a baby, you grow fast until a certain height, like 1 meter 60 or something, and then your rate of growth levels out. That's a polynomial regression. Maths is more complicated. But the linear regression is the most common thing. If you take 100 milligrams of paracetamol, 200, 300, 400, your effect on pain is, increases as the dose goes up. So like a dose response type thing is a linear regression. You've seen R values and so on in papers. That's the description of the strength of that association. So modeling is taking your one bit of data and using that bit of data to predict another bit of data. That's all it means. And regression is the most common way to do that.
Is your R value meaningless without your P value? You've got the strength and you've got...
No, the R value isn't meaningless without a P value because you're not testing a hypothesis as such. What it's telling you is how reliably, if you like, why your one piece of data is predicting the other. So if you have an R value of 0.5, well, it's kind of 50-50. It's okay, but it's not great. If you have an R value of 1, it's 100% reliable. You know, if you have a fasting blood glucose of 10, you definitely have diabetes, for example. Now, maybe that's a bad example because it's an artificial thing, isn't it? We just say you have diabetes over this value. But it's the slope of the line, and so the reliability of the line, if you like. Something to read into a bit more. We're running out of time, and also I don't want to confuse you anymore. So very lastly, all this statistics sounds terribly exciting, complicated. The reality is that computers do it all. You just have to know which test to do. So I use Stata, which I find useful. It's just what we used in Bristol when I was doing my MD. But there's loads of different programs, and each university will have a program, or each trust will have a program that they recommend you use. Just use that. And all these stats programs will do all these tests for you. And I would say, if you have a chance to learn how to do it, it is a really useful skill. Because I can only really do the things I've shown you now on the stats program, but that's why I get on all the papers, because I know how to do it, and no one else does. So it's a useful thing to be able to use stats programs and apply these tests to your data and clean data. Okay, so I recommend Stata just because it's very sort of powerful and easy to use and user-friendly and so on. But if you really hate statistics, then GraphPad is the one to use, because what you do is you give it all the data and it tells you what tests you can do with the data you've given it. It doesn't tell you whether you should do it, it just tells you you can do it if you want to. And so that's quite interesting. R is free, and because it's free, it's a bit more difficult to use because it's based on a programming language called R. And SPSS, I guess most of you have heard of, is the Microsoft one. All right, so that's it for statistics. I've lost track of the time. The clock's disappeared my computer, but we're probably over. Minutes over, so that's not too bad. Any questions online? I'll take that as a no. All right, so next week I think we're talking about papers or posters, or one of the two next week. We'll see how that goes as to what we do with that exactly. But if you think of any questions about stats in the meantime, let me know and we'll talk more. I'm always happy to look at numbers and stuff with people. And enjoy the week. Thanks everybody online.